Today we're going to start looking at some rules for finding antiderivatives so that we can do definite integrals that aren't just geometric figures. So one rule is that if we have the integral from a to b of f of x dx, and we were to reverse the order of our limits of integration, what we end up with is the opposite of that. So if this particular one, a is less than b, when we switch that, we're going to get the opposite. So if f is non-negative between a and b, the integral from b to a is going to give you the opposite value. The next one I think is pretty straightforward. The integral from a to a, you stick your hands together, how much area is there in between them? None. So that's all this is saying. If I start at a and I end at a, I'm not going to accumulate any area. The next one is the constant multiple rule, which works just like constant multiples with derivatives, right? We kept the constant multiple when we took the derivative. Same thing is going to be true for definite integrals. We're going to keep the constant multiple and deal with the rest, which makes sense graphically if we think about it for just a second. Let's pretend that k is, say, 3. I'm just picking some positive number so it's a little easier. If I take the graph of f of x, and let's say that it's all positive, just to keep it clean, and we multiply the function by 3, what does the new graph look like?
It's a stretched out version of itself.
Yeah, it's stretched out vertically, and it's 3 times taller. Well, if it's 3 times taller, won't it have 3 times the area? Now, we haven't changed the width at all, so it's just 3 times taller. So this is saying it's 3 times taller than it was to begin with. The next one, again, just like we had with derivatives, we can do the antiderivatives a term at a time. We don't have to do all of it together if they are separated, if the integrand has pieces that are separated with a plus or a minus. And again, this is just like derivatives. When we have the derivative of x squared plus 3x, we don't have to deal with it all at once. We just deal with the x squared, then we deal with the 3x. This next one is one of my favorites because I can remember a time when it messed with my mind, and then I was like, oh, that's fine. This says that the integral from a to b of f of x dx plus the integral from b to c, notice that this is the same as this. So I think of it as picking up where I left off and then going to c is the same as going from a to c. It's a little bit like I took a trip and I was going to San Antonio and I went from here to Buc-ee's, and then I went from Buc-ee's to San Antonio. That's the whole trip. Okay? The nice part about this is that, and did I lock it? I didn't think that I did. Must have done it out of habit. Sorry about that. I meant to not lock it. The interesting thing about this is it does not matter whether b is between a and c or not. So let me show you the case where it's between the two. So you got a graph like this. Here's a, here's c. This is y is equal to f of x. B is somewhere in the middle. The integral from a to b plus the integral from b to c gives you the integral from a to c. Everybody's perfectly happy with that. What people initially are not happy with is, what if it's like this? Here's a, and b is over here, and c is here. And this is, again, y equals f of x. So if you take the integral from a to b, that's going to be all of this area, right? Plus the integral from b to c, but the integral from b to c, notice I'm going right to left instead of left to right, so it's going to be negative. It's going to subtract that off. So it's going to give you the integral from a to c. It's going to give you this area that's left. So the order is not important in this. When I first learned it, I was like, oh, a, then b, then c. Great. And then it took me a minute to go, oh, what if they're out of order? It turns out it does not matter. So as long as these two match, that's the important thing. You have to, where you quit here has to be where you start here. A property of definite integrals that we don't use very often is this one, and that is if I take the minimum value of f on the interval from a to b times b minus a, so I'm getting an area, that's going to be less than or equal to the integral from a to b of f of x dx, which is going to be less than or equal to the maximum of f times b minus a. Notice these are all areas. This says use whatever the lowest value is times the width of the interval. This one says use whatever the highest value is times the width of the interval. And this one says use the actual heights times all those little tiny subintervals. And then the last one, if f of x is greater than or equal to g of x on the interval from a to b, then the integral of f of x dx has got to be greater than or equal to the integral of g of x, both from a to b. And I think that makes sense. One function is above the other one. That's going to have more area than the other one is. So let's take a look at these. These are general questions I can ask you without asking you to actually do any antiderivatives. So given these facts, the integral from -1 to 1 of f of x dx is 5, the integral from 1 to 4 of f of x dx is -2, and the integral from -1 to 1 of h of x dx is equal to 7. Given those three facts, I can ask you all kinds of questions. Not all of them are possible. So let's take a look. So here I have got the integral from 4 to 1 of f of x dx. Well, we know that that's the opposite of the integral from 1 to 4 of f of x dx. If we interchange the limits of integration, we have to multiply by -1. And I know what this integral is, so that's going to be the opposite of -2 is 2. All right, what can I do to find this integral, the integral from -1 to 4? I've got from -1 to 1 and from 1 to 4. So I can just add them, yeah. That'd be the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. So that's 5 plus -2 is 3. All right, what about the integral from 0 to 1 of f of x dx? Any thoughts? You're thoughtless? So the thing that you're tempted to say is that since the integral from -1 to 1 of f of x dx is 5, that the integral from 0 to 1 of f of x would be 2.5. Not true. Because I don't know that this is symmetric about the y-axis. Now, if I know it's symmetric about the y-axis, then that is true. But I have no idea what f of x looks like. So this is not possible. Okay, so then for this one, this will be 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. So that's 2 times 5 plus 3 times 7 is 31. Number 5 is a frequently missed problem, and it's because students don't interpret this correctly. So since I'm adding, I'll do just like I did in the previous problem. I'm going to add 2 separate integrals together. This would be the integral from -1 to 1 of h of x dx plus the integral from -1 to 1 of 3 dx. The integral from -1 to 1 of f of x dx is 5. And how can I find the value of this integral? It's not piecewise, it's just always 3. So yeah. So it's the height is going to be 3, and what's the width going to be? 2, exactly. So this is going to be plus 2 times 3. So that's 11.
First number should be 7, not 5.
Oh, sorry. It's H, not F.
Bizarre.
Thank you. Notice that that's not the same thing as this. The integral from -1 to 1 of h of x dx plus 3. That's what happens on this one is students think it's that, and they'll just do 7 plus 3. But here the 3 is inside the integrand, so that's part of what we're doing. And if you think about it, if you took a function and added 3 to it, you just have moved it up 3 spaces, right? So now it's going to have an additional area underneath it. And then this one, the integral from -2 to 2 of h of x dx, this is sort of the opposite of the problem that people have on number 3. They go, oh, from -1 to 1 of h of x is 7, so from -2 to 2, that should be 14, which, no. We don't know what it does out there. So this is not possible. All right, page 2. So taking you back to some basic geometry ideas. If we know the area of a rectangle and we know the base of the rectangle, we can find the height, right? The height is going to be the area divided by the base. So what if instead of being an actual rectangle, if the top of the, and again, that's why that's in quotes, rectangle, is a curve, and divide the area by the base, what we're getting is not the height of the rectangle, because there's not a single height to the rectangle. What we're getting is the average height of the rectangle. We're getting something that looks like this, where this is the average height. Basically, what you're saying, and I didn't draw that really super well there, but see if I can make it a little bit better. What we're actually saying is that if I made a rectangle with this height, it would have the same area as this does. Or, to put it another way, sometimes students like this, if I cut this part off and melted it down, it would exactly fit this part. I could pour that extra into this gap here if I have found the average height. Now, the area is found by the integral, right? So, if the curve, that's this top, is described by an integrable function, then the average value of f is the integral from a to b of f of x dx over b minus a. That is, it's the area divided by the base. And even if, so remember, we can have a function that is integral that's not continuous. We did that one with the absolute value of x over x. Wasn't continuous, but we could still find the integrals. If, in addition to being integrable, it is continuous, then there will be a place on that closed interval where the average value of f is equal to f at c. So, let's do this one. Find the average value of f of x is equal to 7 minus x squared plus x on the closed interval from 0 to 3. Where on the interval does f take on this value? This is very much going to be a calculator problem. So the average value of f is going to be the integral from 0 to 3 of 7 minus x squared plus x dx. That tells me the area, divided by 3 minus 0 tells me the base. And so since you don't know rules for antiderivatives for these yet, you'll learn them a bit later. We're going to do this on the calculator. So, oh, didn't mean to push that. So we're going to do the integral from 0 to 3 of 7 minus x squared plus x with respect to x all over 3. And we get 5.5. Oh, that's nice. So that's the average value of f. And then they want, where on the interval does f take on this value? So this feels a little bit like the mean value theorem. We're trying to figure out, well, that has to happen at least once because this is a continuous function. So what we're going to do is go, okay, where is 7 minus x squared plus x equal to 5.5? Again, I tend to set that equal to 0, so I'm going to subtract the 5.5 and have 1.5 minus x squared plus x is equal to 0. I think that finding zeros is just easier. So clear anything that's in there out. 1.5 minus x squared plus x. And I'm going to set my window. Part of what you have to be able to do is graph on an appropriate viewing window. And I'm looking for the zeros, so I'm just going to set my y to go from -1 to 1. And that's a really hideous point. Somewhere between, this was 0 and this is 3, so that's somewhere between 1 and 2. So we'll go to the calculate menu and find the 0. Georgie, we were looking at May's calculator earlier that she was using. It tells you this immediately. You don't have to, you can just trace over to it, and it'll pop right to it and tell you what it is. You don't have to do this left, right, stand up, sit down, fight, fight, fight. These are always fun to guess. I'm going to guess 1.83. That was a really good guess. It was 1.822 or 1.823. All right. We'll round it. Truncating makes some of my students itch because you've been rounding all your life. The idea that you can just toss that, cut it off and toss it away is irritating to many people. Okay, any questions? All right. So let's look at page 3. So consider for a second a plane flying at a constant ground speed of 120 miles an hour from noon until 6 o'clock p.m. What does the integral from 1 to 4 of 120 dt tell us? Well, this is our rate of change, and we're doing that over this time interval. So if you think about it, so this is the velocity in miles per hour. It's always 120. And we're going from 1 to 4, and this is hours. So this is going to be 360, and what are the units going to be? Yeah. Because I'm multiplying the miles per hour times the number of hours. So this tells us that from 1 p.m. until 4 p.m., the plane travels 360 miles. Which is the integral from 1 to 4 of 120 dt. It's telling us the change in position. Okay, or if you wanted to use the physics term for it, the displacement. Now, let's make this more general. Let's say S of t is the position of the plane at any time t between 0 and 6. Then its velocity would be S prime of t, right? Which is v of t. So what does the integral from 1 to 4 of f prime of t, or v of t, either way you want to say it, tell us? Well, if we were doing the integral from 1 to 4 of s prime of t dt, that is the integral from 1 to 4 of v of t dt. And in our previous example, it gave us the displacement, right? It's going to tell us s of 4 minus s at 1. So it's telling us the change in position. That is the displacement from 1 p.m. until 4 p.m. Now, this is a physics example, but it's much broader than that, as it turns out. So if we interpret the integrand remember that's what we're taking the integral of, as a rate of change, f of t, with antiderivative, capital F of t, then the integral from a to b of f of t dt is capital F of b minus capital F of a. I prefer to think of it this way. The integral from a to b of f prime of t dt is f of b minus f of a. We'll get more into that in a future lesson. But for now, what we need to know is if we're going to evaluate this definite integral, and they don't tell us much about it, we have to find an antiderivative. We haven't gotten much in the way of rules for antiderivatives, but let's take a look at this one. So what can I take the derivative of and get positive sign? Negative cosine. So this is going to be negative cosine at pi minus negative cosine at 0. So this is going to be the opposite of cosine at pi is -1, exactly. Minus the opposite of what's cosine at 0? 1. Hey, look, that's 2. Which is the fact we used in a previous lesson where I said, given that this is 2, well, now you can find that it's 2 all on your own. Okay? Questions? Okay.